Okay, hey, thanks for listening today. Want to thank Hyperion and the HPC User Forum group that puts these events together. They're excellent events. And 1.5 years ago, one of my colleagues, very senior person in IBM Quantum, Jay Gambetta, gave a presentation on quantum computing and IBM Q at this event 1.5 years ago. And that was part of an excellent day on quantum computing that Hyperion had put together. And so I'm going to try and update you on some of the things that have been happening. A lot of good stuff is happening in the field. IBM's very active, and I'm going to tell you about some of the new stuff and some of the updates there. And how many folks here have actually used real quantum computers at any time? All right, hey, follow the man's lead. So I'll tell you how you can use actual real quantum computers. We've had them on the cloud now. We're in the 4th year. I'll also tell you, high-level quantum computing, IBM Quantum Computing Systems, the IBM Q Experience KISS kit, which is our software development kit, the IBM Q network, and quantum volume. So we've got a lot to cover. And okay, so quantum computing, very, very high level. I'm not going to try and get too deep here, but the computing that we do now, whoops, wrong button. The computing that we do now, which is on the left, okay, it's based on transistors. It's the ones and zeros, a whole bunch of them. It works really well. We've been doing that for years and decades, and that's why we have our servers and our HPC systems. Quantum computing, doesn't use that. That's representing the world in a couple of complex numbers at the same time. That's where the superposition of your quantum bits is reflected. When you measure those qubits, you actually affect them, so you have to be really careful. You might want to entangle a couple of qubits for certain gates, and when you do that and you try and measure one qubit, you're actually affecting the second qubit, so that's not so easy. Quantum gates are the basic unit of doing your computation. So, on the left-hand side, the world is really, really good at that. Been doing it for several decades. On the right-hand side, the quantum computing that's new. And IBM and organizations and individuals are still learning how to do that, still inventing that. Why would we want to do something like that? Well, as an example, we all love the caffeine molecule, right? Most of us take advantage of it. If we were to completely model the caffeine molecule, and it's not all that big, okay, with a quantum computer, we could do that with 160 logical qubits, right? Perfect qubits, logical qubits, not physical qubits. If we were to represent that with bits, we would need 10 to the 48th bits. That's a pretty big number. And if we were to make a classical computer to do that, it would be somewhere 1% to 10% the size of the Earth. And that's not going to happen, right? And caffeine's not that big of a molecule, so when you get into harder problems of larger molecules or optimization problems or machine learning, we can do great things with our classical computing, but there's reasons why we're going to want to use quantum computing. And we do have them now, right? As I mentioned, we're now in our 4th year of making quantum computers available at the IBM Q Experience. This is a couple of units. See if I can use this time. This is a couple of units you can see, in those white, cylinders. We'll look at a cutout. I think this is in our Yorktown facility. I'm not sure if these are research units or these production units, but they're there. They're working, they're running. One of the things that we've announced since 1.5 years ago is we'll be establishing a quantum computation center. We're getting that ready in our Poughkeepsie site, so that will be for production use, for client use, for the IBM Q Experience, and we'll still do research and development at our IBM research labs. If you were to crack one of these things open, take a saw to it. You can see over here, there's the qubits. I think this is a 2-qubit system. Those little wavy lines are where the microwaves are delivered to the quantum bits. These are superconducting quantum bits. We make these, we manufacture the things in-house. The quantum processor, you can call it, is down there on the lower left hand. And then that goes at the bottom of the unit, the cryostat at the very bottom. And the cryostat construction is doing a couple of things. One is it's making it very, very cold, 15 millikelvin, to keep them, kind of quiet and calm. Also, you can see a bunch of wires, and that's delivering the microwaves to the qubit. So every qubit in our systems are individually controlled. You've got two lines going in. One is to set up the quantum state, and one is to actually read the quantum state. And all of that is done by the equipment, on the right-hand side. Your, software to, set up your algorithms, to run your applications, that you're actually putting on the right-hand side. So this is pretty different, right, than the servers, than the computers that we're used to from the last many, many years. Another announcement is in January this year was the IBM Q System 1. So this is, the first unit meant for commercial use. So this can kind of be put down, in kind of any data center. There'll be an IBM, data centers, but it's, a modular construction. It's about 9 feet by 9 feet. Once you set the system up and you get it running, it just kind of runs, and you monitor it and you maintain it remotely. I've actually got a chance to walk around one of these things. It's pretty cool. It's, quite an impact there. And in fact, yesterday, we'll tell you a little bit more about the IBM Q network, but an announcement was made that the Fraunhofer Society, hope I said that properly, has reached an agreement with IBM, and an IBM Q System 1 will be delivered and deployed to IBM Germany. So that'll be the first time one of these will be running outside of the United States. Okay, so we've seen, some different systems, our commercial system here. Okay, well, I told you it's 9 feet by 9 feet. A lot of these presentations were talking about performance, right? How powerful are these things? So to simply count the number of qubits is pretty meaningless. That doesn't mean anything, different quality of them. Okay, how do you run it? So we've come up with a performance measure procedure called quantum volume. And, yesterday we heard a phrase, LINPACK Q. Well, maybe this is, the future LINPACK Q. And quantum volume is how do you measure the performance of a system, and it's basically looks at 4 different things. One is the number of qubits. A number is what is the connectivity of them, what kind of topology do you have. Another is how many operations you can run in parallel, and another is how many gates you can apply before, the errors accumulate, and you've effectively got a system which is working classically. So quantum volume, it's a procedure. You actually set up an algorithm, and you run it many, many times, and you get your number. We've got a couple of papers on this, if anybody would like those papers. One is just kind of describing what it is, and another is presenting some of the results that we've produced. Drop me an email, let me know. And we've seen a doubling in quantum volume now over the last, into the 3rd year. So in 2017, that was a device at the IBM Q Experience. It made 4. Then we had another device in 2018. It made it to 8. And then we attained and announced this year that the IBM Q System 1 actually made it to 16. And we would like to see a doubling of quantum volume in the years to come. There's a lot of things, right, in terms of the qubits and the whole architecture and the whole system to make that happen. We believe we have a roadmap for that. But if we're able to get to what we call quantum advantage, and quantum computers are really helping provide benefit to businesses and organizations, we're going to have to keep up with that doubling. Okay, so we've talked a bit about the systems, we've talked a bit about the performance and the doubling of quantum volume. You run these things, our things, with Qiskit, a set of software development tools. It's available at GitHub. It's open source. If anybody would like to, get involved in it, contribute to it, you're more than welcome. If you have particular ideas, you could, contact me. We could talk, or put you in contact with the team who oversees this, takes care of this. Right now we've got kind of 4 modules. I mentioned it's open source. It's written in Python 3, so it's a bit familiar. The foundational tools is the Terra, so that's where you create your quantum circuits, and you control the individual pulses. Ignis is tools for characterizing and mitigating error at the individual qubit level. People who use these systems, outside of the company, they're really excited about this, right? Because you actually do want to know what each individual qubit is doing if you're getting pretty sophisticated with thing. Aqua is a library of applications and algorithms, I should say. That's something within this year as well, so kind of abstracting things up another layer. And we also provide, as part of Qiskit, a simulator. And simulators are very useful. They have their use. There may be a first step, but I can see the luggage. A lot of folks here are going to go back and get on an airplane today. And how many of you would like to get on an airplane and the pilot comes on, folks, welcome aboard. I'm really excited because I've just been flying simulators and today's my first time actually flying a real airplane, right? Everybody be, bolting for the door. So when you're at some point you got to be using the real machines, right? If you want to be developing your algorithms and your applications, okay? Qiskit is available at GitHub for download. There's been over 145,000 downloads. It's actually now available at the IBM Q Experience, which I'll show you very briefly. Again, if anybody, it's open source. If anybody would like to, get involved in contributing to it, that would be wonderful. IBM Q Network, so various organizations participating in that. There's a lot of names here. A year and a half ago, there were maybe 30 names or something. This is as of 13th of July. So there's at least one more now. Kind of looking through this, you can see Argonne, thank you. You can see Oak Ridge is there. Startups are interesting because they're trying to figure out how to use quantum computing. They're accessing our machines for particular algorithms or applications. There's different types of research going on at the academic level. Some of that is focusing on, well, how do we build skills? How do we teach, right, quantum computing? The world has to learn how to use these quantum computers. Hubs provide it to other entities and industry partners. Doing some pretty serious work there. Exxon joined as an industry partner early in the year. Air Force Research Lab was, a few months ago. Kind of some examples of, I think you can get. There's some other financial companies here, like in Japan. I think you can sort of get an idea what are maybe the earlier use cases and applications. Some of the things I want to say, like what's being done is speeding up applications in quantitative finance, trading simulations such as derivative pricing, molecular modeling that enables discoveries like more efficient batteries, novel paths for production or transportation route optimization, or better patterns within AI and ML processes. So maybe you want to sort of group those together, and physical processes, chemistry, physics, scenario simulations, better optimization, and AI and ML. Okay, keeping an eye on the time. So IBM Research also published a couple of papers that made the cover of Nature magazine, which is kind of a big deal. One is using IBM Q systems for chemistry modeling, and you can see here, for example, this is 2018. Compared to what was used of a device in 2017, it was 10 times better. And if you look up here, you'll notice that the experiment was run just on 4 qubits. You're not always using every single qubit on the processor. A lot of work is done, with just 1 or 2 or a few or something like that. So, here's an example of chemistry. Here's one about machine learning. What they did is they proposed and implemented 2 methods to represent the feature space of a classification problem. They took advantage of the large dimensionality of quantum Hilbert space to come up with an enhanced solution there. So a couple of covers of Nature, that's pretty good. It's not just IBM which is doing research and publishing on using IBM quantum systems. So far, over 175 third-party papers have been published that cite the use of IBM Q systems in the work. Okay? If you'd like to play around with these, go check out the IBM Q Experience. That's where the systems are available. That's where Qiskit is now loaded up, and you can use it. You can do a couple of things. There's a circuit composer, and you can also do coding like with Jupyter notebooks, for example. Here's you can type in the coding, you can copy paste the coding. Here's a visualization tool that you can see. Here's the circuit composer. Some folks like using this if you're new to quantum computing, just to sort of get started, help you visualize and change it as you go along. Also starting a brand new algorithm. It can be kind of a nice way to help you sketch some of that out. Here over on the right-hand side, you can see some of the machines which are available. So, here's the simulator, right? Remember the pilot. Here's a couple of 5-qubit machines. Here's a 14-qubit machine. Also, a couple of weeks, we deployed another one, Orense, and just at lunchtime, I was looking at the calibration figures, and it's notably better than, the other devices at the bottom of that screen. So, those are the real machines. If you go in and you click on, well, you don't see it here, but you can see, the C0 error rates, the single gate error rates. We publish them right there. Talked about the downloads, the papers. Over on the right-hand side, actually the new number is now 28 million experiments and simulations have been run at the IBM Q Experience. The numbers, always going up like this. Actually, more has been done with the devices themselves than the simulators. It passed that point sometimes this year. And we recently announced a new feature where you can schedule time. So you can have the device, have part of the device. I'm not sure the specifics. Or if you're an educator and you want to be, showing these, you can schedule the time. A lot of stuff available in the community. Public Slack channel. A lot of action going on there, a lot of discussion. Send you the link. Again, we talked about the device, Qiskit, quantum volume, the IBM Q Experience, the IBM Q network. If any of that catches your fancy, you have any questions, you'd like some more information, just drop me an email and either I can point you somewhere or if you want to get involved, I can point you to the smart people or connect you with the right people. So a little bit over. Hope you enjoyed that. Maybe time for one question and then I'll get out of your way. Well, it's going to be an IBM Q System 1. At this time, the largest that we have announced is 20 qubit systems. Obviously, we're always, making them bigger and better. I do not know what will go to Germany. Right? Yeah?
One quick one. So when quantum computers mature or are more mature, do you see them as complements to classical computers or replacements?
Oh, for a long time, they'll be complementary, right? I mean, they will reach a point where there's certain problems that they'll handle better than classical computers, but there's other problems where nobody is really thinking about them, replacing ever, Yeah.
But just actually to make sure, so the 22 qubits are all usable. It's like all virtual qubits or something like that, right?
So it's 20 physical qubits,
20 physical qubits.
And they're all usable if you need to use them all. And those are available on our premium systems. At the IBM Q Experience, the public system, I think the most available right now is what you saw, the Melbourne, which is 14.